it's my great pleasure to talk a little bit more about that. I'd like to welcome up Eric Starkloff, our Vice President of Product Marketing, to talk about these tools and platforms. Have a great 2012 VIP. Thank you very much.
All right. Thank you, Francis. Guten Morgen. It's fantastic to be back at VIP Days in Germany. I have a question for all of you. The projects you're working on now, are they simpler? Are they easier than they were 5 years ago? The embedded systems you're building, are they less complex? Are they more complex? What about your test systems? I'd be willing to bet that for all of those, the answer is they're more complex, right? And that's a challenge that we all face as we try to build, design, and test these systems. Now, fundamentally, that complexity is driven by this phenomena that we all know, Moore's Law, the doubling of transistor densities, every 18 months. And this law has continued to hold true for decades now. If you look back, a comparison to 1976, that happens to be the year that NI was founded, until today, the amount of transistors on a typical microprocessor has increased by a factor of 400,000. What have we done with all that processing power? Well, we've used it basically to put more and more sophisticated software on all of the systems that we design, build, and test. That complexity of the software is illustrated in one dimension by the lines of code in some of these typical embedded systems that I have going behind me. And it's really just unbelievable how complex these systems have gotten. And we're all familiar with this because we live and breathe this complexity and work every day to try to tame it. Now, what we've basically done across all these applications, if you think about it, is we've digitized them. We've turned them into digital challenges. We've taken systems that oftentimes were traditionally mechanical, and we've turned them into electromechanical systems with lots and lots of software capability. Just to take one example, here's an old engine. I thought showing this in Germany, I might get some weird looks at an engine that old. But think about the engine. This used to be a mechanical system, completely a mechanical system. And if you were going to work on an engine like this a few decades ago, what tool did you reach for? It's a wrench, right? It's a mechanical system. You reach for a mechanical tool. Well, the world's changed quite a bit, as we know. Here's a modern engine. And if you're going to work on this, if you're going to debug or repair this engine, what do you reach for? Well, if you're me, you take it to the dealer. But if you were so inclined to work on this yourself, the tool you would reach for would be a laptop. You would plug it into the diagnostic port of the ECU, download the error codes from the software that's running on that engine. That's where you would start. And so this is just one example in automotive of how we've digitized an application. We've created incredible complexity, but also we've used this to create better systems, better safety systems, more efficient systems. Now, while Moore's Law kind of creates this challenge for us, it also provides one of the potential paths to the solution, right? If we can build on all of this powerful underlying technology, if we can use software in a way to design these systems and to test them, then we can, as I said, tame Moore's Law. We can ride that same curve. Now, another question for you. Over the last 5 years, has your team and your resources, have you gotten more resources? Or has it stayed the same or gotten smaller? Right? That's the other tension that we have. We have these more complex jobs to do, but for most of us, we're doing it with the same amount of people, sometimes less people. And that's another trend. Now, the only way to address this, then, is this concept of abstraction. We fundamentally have to be able to provide more abstraction over time in order to create ever more complex systems with the same or fewer resources. It's imperative. And so in areas like software design, we're seeing higher levels of abstraction as a trend. We have to be able to have system-level design to create these systems, to verify them, and to test them. This is a trend throughout many different applications. Here's an example of this trend in typically embedded applications. So it used to be that the domain expert worked with a team of implementers. right? So a domain expert understands the application, and then to actually implement the embedded system, you have an analog engineer, a digital engineer, software developer, and so forth. And this is changing. This is evolving to where now often a domain expert works with one or a couple system-level designers. Or probably, sometimes, like probably many of you, that domain expert can implement the system themselves with a high-level abstraction, as many of you do with LabVIEW. This is a trend across a lot of industries. There's a quote there from the Harvard Business Review about how innovation is happening with smaller and smaller teams than it did, over the past decades. Now, we have our own data to support this trend. So we've done a research study over the past months and looked at people using these higher-level abstraction tools, in our case, LabVIEW, for building embedded systems, and compared this to a group of people that are using traditional embedded design tools. And the results that are shown behind me are that teams using LabVIEW are able to be half the size and get the project done in less than half the time for building their embedded system. So it's clear that these higher level abstraction tools provide a tremendous gain in productivity, and that's absolutely required to keep up with the challenges that we all face. Now, another trend that we see that's addressing this issue of complexity with less time and less resources is more integration between the functions of design and test. And that trend is often represented by this diagram, this V diagram. On the left side is the design process, starting at a system level and drilling down into levels of detail. On the right side is a corresponding test function, starting at the detailed level and going up into system level test. The point of the V is that there is a corresponding test function for each part of design. It also implies a system level approach, and it implies common components for testing that start very early in the design and simulation and go all the way through final test. And so as we look at how design and test have become more integrated, what I see is that often these functions start to be a little blurry. It's difficult to see the difference between where the design process, say, stops and where you're doing testing. We'll show you a product tomorrow. You can see we've got lots of toys behind me that we're going to be demonstrating tomorrow. We'll show you a product that illustrates this, I think. It basically is an instrumentation product that has all of its firmware designed in software and open to the user through a programmable FPGA. You can drill into this firmware layer by layer and get all the way down to the pin of the device, the finest level of detail. Now, what this means is that you can go in and customize it for different test or measurement applications. That's one part. But it also means that you can replace that firmware with different functionality and use that same piece of hardware as a prototype or as part of the embedded system. This is what I mean when I talk about the lines between test and embedded design becoming blurry. And if you take this view of the world where these things come together, well, then you can have a common platform to address both sides of the V. Sorry, go back one slide there. So this approach we call graphical system design, right? And that common platform for National Instruments is built on a high-level abstraction in LabVIEW. And it's LabVIEW combined with different hardware products that is able to serve many, many different types of applications. And it's that combination, it's that platform that can address both sides of this V, both designing embedded systems, measuring and testing them as well. Now, that quote that I just previewed a second ago is one that I use a lot. And it's basically, the point is, this isn't just a futuristic concept. It's something that happens in the here and now. And this quote by William Gibson, a science fiction writer, is that the future is already here, it's just unevenly distributed, right? So we can get a glimpse of the future by looking at some trends that are here today. So I want to show you a few examples to make the concept hopefully a little bit clearer. Here's an example of an application that's fundamentally an embedded application for a radar system. So the truck on the right there is the actual radar, a deployed radar system. So this thing can drive into an area, it can deploy its antennas, and it can start operating the radar system. The picture on the left is what's inside of that van, right? So this is actually the receiver of that radar system. And it's all done in PXI LabVIEW with FPGA processing cards. Now, the top two chassis there in the picture, that's the actual receiver. So that's connected directly to the antennas, receiving the signals, doing lots of signal processing to get the radar cross-section of the targets. The bottom chassis, well, that's actually the test system. That chassis generates the scenario signals and calibration signals to test the receiver. Now, it's kind of a blurry line between the two, right? They use the same components, they use the same software. Part of it is basically the embedded system, and part of it is the test and measurement system. Here's another example. This is one we showed just a couple of months ago at NI Week. This is an embedded system in the medical area. It does laser eye surgery for cataract replacement. Now, this system was originally prototyped using our data acquisition products and LabVIEW to start to figure out how to perform this laser surgery procedure on a patient. The actual deployed system uses those same components. Inside of that machine that goes in the doctor's office or in the hospital is LabVIEW running on data acquisition cards with the core control logic running in an FPGA that controls the laser. Right? So now the line between this prototyping system and the deployed system is also pretty blurry. It's the same capability. And finally, here's an example in engine control. In this case, this is about creating more efficient software for engine control. In this application, we basically took this motorcycle and put a compact Rio system on the motorcycle to do measurements on all of the signals around the engine, right? So acquisition of the sensors and measurement of all of the parameters of the engine. Drove the vehicle around, collected all of that information as an embedded data logging system. But then we actually the customer took out the factory ECU and wired those signals directly into compact Rio, took the information from the measurements to create a model and to create the control code in LabVIEW, run it down on the real-time processor and FPGA and compact Rio, and replaced the factory ECU with that system, drove the motorcycle around, and were able to rapidly change and adjust the control program to test the performance of the vehicle under these different conditions. So again, this thing went from a measurement system to an embedded control system, and the only change was the software. The exact same hardware platform was used. So this is when we talk about the combination or the integration of design and test. This is what we mean, these areas where you can use the same hardware platform and just change the software to get different capability. And fundamentally, that's the type of abstraction that allows you to meet these challenges of getting more complex designs, more complex test systems to market with fewer resources and in less time. So this is VIP, right? It's virtual instrumentation in practice. And so you're going to see a lot of examples of these kind of applications throughout the next couple of days. We'll be showcasing applications in the sessions, up here in the keynote stage. You're also, as I mentioned, going to see a lot of products and the innovation that NI's been working on. Michael, I believe, showed the innovation or the investment in R&D. We spend over $200 million a year in R&D, and we're going to be showing you over the next couple of days some of the fruits of that labor in new product capabilities to help support you create these next generation of embedded systems and test and measurement systems. So I look forward to a fantastic next couple of days here at VIP. Thank you very much for your time, and enjoy the rest of your day.